Our first speaker is Adrian Barker. He's an associate professor in applied mathematics at Leeds, and he's been there since 2016. His research interests include astrophysical, fluids, waves, instabilities, and MHD. And today he's going to talk about tidal dissipation in stars. So thank you, Adrian.
There we go. Yeah, so I thought I'd talk about tidal dissipation in stars. So I guess it's what I spend, most of my time working on tidal flows, but not all of my time. But I guess it's what I've worked on the most in the past, and I guess now, but maybe that's less so now. So I'm going to talk today about tidal dissipation in stars in particular, and work done in collaboration with various other people in Leeds. So mainly actually work done by my PhD student Craig, who's now moved to Newcastle as a postdoc. And former SDFC-funded postdoc Jeremy Vidal, and current postdoc Aurelie, who's here at this program, and also with Chris Jones as well, who's also at Leeds. And I'll talk a little bit about a number of the papers on the right, which I won't talk about all of these, so don't worry too much. I'm not planning on presenting that much work in this talk. So the motivation for this is that gravitational tidal interactions drive spin and orbital evolution in planetary systems with close-in planets, such as hot Jupiter systems that have roughly Jupiter-mass planets that orbit their stars in less than 10 Earth days. And also in binary star systems, then gravitational tidal interactions can cause long-term evolution of these systems as well. And now is an exciting time for this field because we're actually able to detect, at least infer, possible evidence for orbital decay in some of these planets. So one of these is one called WASP-12b. And in this system, we've inferred a change in the period of the planet of about 30 milliseconds per year from observations that have been done over a decade or so, which can, if it's tidally driven orbital decay, that corresponds with orbital decay in about 3 million years. So to indicate how we can do this, this is just showing on the right for a different system, the transit light curves, so looking at the light from the star and looking at the dimming in the starlight as the planet passes in front of the star. And this is a system that's been observed for over a decade or so, and we can start to look for shifts in the center of the transit. So if the transit is occurring sooner and sooner, so if it shifts kind of towards us, then that can be interpreted as evidence of orbital decay of the planet, if you can rule out various other explanations. And in particular, the formula at the bottom is just based on energy considerations, really, is what the shift of the center of the transit would be if you had a circular orbit. And essentially, there's the planetary and stellar mass ratios. There's, if I can find my mouse pointer, nope, okay. There's the stellar radius and semi-major axis and the orbital period. So these are things which you can constrain from the observations. And then there's this parameter Q, which is essentially a dimensionless inverse measure of the efficiency of tidal dissipation. And that's what we can really constrain by these observations if the shift in the center of the transit is due to orbital decay of a planet. And this is what we want to determine theoretically to determine how efficiently tidal flows are dissipated in stars, because the consequences of that is that determines the rate at which the planet would spiral into the star. So note that these systems are the opposite of the Earth-Moon system in that the planets orbit their stars at a faster rate than the stars rotate in most cases. So the stars rotate with 20 or 30-day rotation periods, whereas the stars orbit in about 1 day. Which is the opposite situation of the Earth and the Moon, where the Earth rotates faster than the Moon goes around us. And that leads to the opposite direction of the tidal evolution of the orbit. So in fact, it causes the planet to spiral into the star due to this mechanism. And this system on the right is actually one where we've actually got constraints. We essentially, don't have efficient orbital decay. So we've looked at the residual, that's the difference in the center of the transit from the prediction assuming a constant period. Then you can see over a decade or so, that's about 3,000 orbits or so, then you can see essentially no significant shift in the center of the transit for this system over that period. Whereas if you had tidally driven orbital decay, it would cause the residual to follow, for example, one of these lines, depending on how efficiently the tide is dissipated. So these observations can constrain the mechanisms of tidal dissipation in stars. But I'm interested in not the observations themselves. Well, I don't do the observations myself, so I'm interested in looking at the theoretical mechanisms behind this. And Another application for tidal dissipation in stars is in binary stars, and in particular in roughly solar mass binaries. Then we know from looking at the eccentricity distributions of these stars, this is just showing one example from M35 on the right. So it shows a range of stars with different eccentricities, different binary star systems with different eccentricities as a function of the orbital period, or log of it in days. And you can see that the ones inside of 10 days have a strong preference for circular orbits, so eccentricities of 0, whereas those outside of 10 days have a wide range of eccentricities. And very roughly, you can separate the region in which you have primarily circular orbits from those being primarily eccentric as being the so-called circularization period. And this is found to be a function of stellar age over the cluster. So this is indicating ongoing tidal dissipation on the main sequence for these systems. And again, if you just look at the energy dissipation in the star, then if you can calculate the time scale for the orbit to circularize as a function of this dimensionless measure of the efficiency of tidal dissipation, this quality factor Q. And from theory, we want to determine what that is. But from observations, you can use timescale arguments really to determine, to put constraints on this. And we do have observations that this is tidal circularization is ongoing on the main sequence and it's not primordial. So I'll come back to this perhaps at the end. So that's just to motivate two different applications for what I'm going to talk about. I'm mainly going to talk about the exoplanet applications, but I'll also talk about the binary star system as well. And most of what I'll talk about will focus on one particular mechanism of tidal dissipation. But before I get into that, what we need to do to understand tidal dissipation in stars is to understand tides in both convective regions and in radiative regions. So for most stars that host planets are usually in these mass ranges here, so M, K, G, and F type, which is kind of useless terminology, but essentially it means stars from about, well, I'll consider about 0.1 to 1.6 solar masses. So less than about 0.4 solar masses are fully convective. So we need to understand tidal flows in convection zones. And stars that are about 0.4 to about 1.1 solar masses have a radiative core like the sun and a convective envelope. And in these stars, the radiation zone can be important for the tide. And we also have F-type stars, which are ones which are a bit more massive that have convective cores as well. And in this case, there is a radiation zone that's sandwiched by convection zones. So later on, I'll talk about the application of tidal theory in simplistic ways, but up-to-date tidal theory using mesostellar models. But before I do that, I'll talk about some more detailed physics of tidal, review the basic physics of tidal dissipation in stars, and then discuss the physics of tidal dissipation in convection zones in particular, and one particular mechanism. So usually the tidal response is decomposed into two components. One of these is a large-scale equilibrium tide, which is essentially, you can think of as a large-scale quasi-hydrostatic deformation of the body, so an ellipsoidal bulge, and the associated flow that with that bulge. And there will be a flow in even if you have a circular orbit, if the spin of the star isn't synchronous with the orbit, which is the case for these hot Jupiter systems. So there is a flow in the orbital frame. And this flow is dissipated it's long been thought to be dissipated by its interaction with turbulent convection in convection zones, which is thought to act as an effective viscosity. And this goes back really to, in the modern guise in stellar binaries, in papers by Zahnd in the 1960s, and Goldreich and Nicholson and others since then, but mainly using phenomenological arguments. So actual simulations of this haven't been done until just over the past decade or so. So I'll mainly talk about this mechanism in this talk because it's one that's theoretically uncertain, and there's a controversy that goes back to the 60s and 70s regarding this. And it's something that I've been quite interested in over the past few years. So equilibrium tides can also be damped by nonlinear tidal effects. So these are ones that rely on the tidal amplitude not being infinitesimally small. And these are effects like the elliptical instability, which can drive turbulence if the tidal amplitude is large enough. So I won't talk about that mechanism because for the examples I'm talking about, that's probably not the dominant one. But it is worth studying, particularly for tides in planets, giant planets that orbit the stars very closely. There are also wave-like tides, which are tidal excitation of waves restored by various different restoring forces. So Coriolis forces, if the star is rotating rapidly enough relative to the tidal frequency, And these are the associated waves or inertial waves that exist in convection zones that were reviewed nicely in the talks in the first week. And this mechanism is likely to be important in stellar binaries, but it's probably not important in most of the hot Jupiters we're observing today. And the reason for that is that these waves only exist if the frequency is less than twice the rotation frequency of the star. So if the tidal forcing frequency has to be low enough to be able to excite these waves. And most of these hot Jupiters have stars that rotate too slowly to excite these waves when you have a planet that's only on a one-day orbit. But even for hot Jupiter orbital evolution, they could be important in young stars that are more rapidly rotating. But I'll come back to this point and indicate this is probably the dominant mechanism for binary circularization. And this is just showing a simulation of these waves on the right to indicate the structures of these. But if you attended the lectures in the first week, then you've already seen more sophisticated figures than these, at even lower Ekman numbers. So the other wave-like tide that we can have is in radiation zones. We can have internal gravity waves, and tidal forcing can excite these waves in any radiation zone, but it can be particularly an important mechanism for the stars I'll talk about in solar-type stars that have radiative cores where the waves can reach the center of the star. And the reason for that I'll talk about briefly later. It is essentially that the waves can reach large amplitudes at the center, and so they can break and be efficiently damped. So I'll come back to these two mechanisms a little bit at the end in relation to application in stellar models. But most of what I'll talk about is looking at the physics of the interaction between tidal flows and turbulent convection. So I'm going to move to a quote by Zahn in 1989. So to summarize, the main weakness of tidal theory when applied to stars with convection zones in general resides in our limited knowledge of the dynamics of the convective motions and of their interaction with the tidal flow. So I think that's still true today, although from just over the past decade or so, we've started to do simulations of this, and the theory is becoming a bit more developed, but this is still a very uncertain topic. So that's what motivated a lot of what I'll talk about today. So I'm not going to go through all of the old arguments in the 1960s and 70s, but I will discuss the basic problem. So the basic idea is that turbulent convection in convection zones is thought to act as an effective viscosity that's much larger than the microscopic viscosity of the fluid in damping large-scale tidal flows. So if you just had microscopic viscosity, then it would play essentially no role in tidal evolution in these systems, and that tidal timescales would be much longer than the stellar ages. So the idea is that the convective motions can act as an effective viscosity. And there is some evidence that this is true, but there has been a long-standing controversy over the efficiency of this when the tide is rapid, so for fast tides relative to the convection. So if the tidal frequency is much larger than the convective turnover frequencies, then it's thought then that the convection will be less efficient at damping the tide. And there's phenomenology in the 1960s and 70s that have looked at how much it should be damped, how much the effective viscosity should go down as the frequency is increased. And that's really essentially the status of the field was based on which of these is true. You'd adopt one or the other and look at how the results depended on that. But it's only in the past decade or so we've been able to study this in simulations, or at least that people have tried to study this in simulations. So the idea is that if you don't have any frequency reduction of the effective viscosity, then the idea is you might be able to use mixing length theory to use mixing length convective velocities u, length scales L, and calculate an effective viscosity by just taking the product of these and dividing it by 3, by analogy with kinetic theory. So the factor of a third is arbitrary, and there's another arbitrary factor, well, not arbitrary, the kind of the key point of what I'll talk about at the beginning is to determine the power law that determines the reduction of the effective viscosity as a function of the frequency of the tidal forcing. So why does it matter to do this? So if you don't have any reduction in the effective viscosity and you use mixing length theory in a star like the Sun, then if you have a hot Jupiter on a one-day orbit, you predict it would orbit and spiral into its star in about of order 100 million years or a bit less. So it would happen within the main sequence lifetime. If you use this linear reduction, so 1/omega reduction that Zahn proposed in the 60s, then you get an in-spiral time for the planet of about 1 billion years or so. Whereas if you use the Goldreich-Nicholson reduction, which is a quadratic one, so more rapid reduction at high frequencies, then this predicts essentially no evolution of the planetary orbit over the main sequence lifetime. So the in-spiral time is about 250 gigayears. So clearly it's important to determine which of these is true, if any, because it does make has significant implications on the orbital evolution of planets. So if you're looking at eddies at the base of the convection zone of the sun, the turnover timescale is of order a month or so, whereas the tidal periods for these short period planets is of order a day, or half a day if you've got a one-day orbiting planet. Then that leads to this ratio being of order 40, this ratio of frequencies. So it is reasonably large, although not as large as it is in Jupiter due to its moons. So in that case, the turnover timescale is much longer, and you can get ratios of of order a few hundred here. So it's important to determine how the effective viscosity depends on frequency to be able to make predictions for tidal evolution in these systems. And it wasn't until some papers by Penev in the late 2000s and then Ogilvy and Lazure in 2012 that people tried to simulate this directly. And there's also been some asymptotic linear analysis of this for high frequency tidal forcing applied to simple flows, which predicts a viscoelastic response of the flow with an effective viscosity, so that the viscous component of that, which does scale as the frequency to the -2. So it's consistent with the Goldreich and Nicholson result, but not actually for the same reasons. So what I'm going to talk about now is simulations to determine this using both local and global models. But before I do that, and I'll illustrate what an equilibrium tide is. So if you've got a slowly rotating star that's in hydrostatic equilibrium, then you can just assume hydrostatic equilibrium at the top left, where P is pressure, rho is density, and phi is the gravitational potential. So neglecting the centrifugal effects. On the top right, we've got the Poisson's equation. And so the idea in linear tidal theory, if we've got small amplitude tides, is we're going to perturb the star with a small amplitude gravitational potential due to a companion planet. And typically it's the L equals M equals 2 component that's the most important. So the quadrupolar tidal potential, which has the form of proportional to, with psi proportional to r squared y22. And if you use linear theory, you can then determine the linear response in the star. And this can be a difficult thing to do. But what we'll do is look at one particular limit of this, which is the equilibrium tide. And the idea is that we're going to take a low frequency approximation of the tidal response. So neglecting any wave-like response. And essentially, in the limit of low frequency tidal forcing, we can ignore the inertial terms on the left-hand side of the momentum equation. And what we're left with is the terms in the bottom. And from doing some operations on this, you can determine the density perturbation associated with the equilibrium tide based on the properties of the unperturbed model together with the imposed tide and the perturbation to the gravitational potential. And you can also determine the pressure perturbation and the gravitational potential perturbation, which can be solved with appropriate boundary conditions. So this is all quite standard, but what is a little bit trickier is the associated flow that you have in a convection zone, which has actually been a bit controversial. So the idea is that in convection zones, normally you have efficient convection, so it drives the buoyancy frequency to be close to 0, or n squared to be close to 0. So you have an adiabatic stratification. So strictly speaking, this is likely to be non-zero, where it has to be to have some convection, but negative, except near the boundaries of a convection zone where it can be a bit larger. But throughout most of convection zones, this is thought to be close to 0. And so it means essentially we don't have any buoyancy forces. So for the purposes of the tide, we often ignore the buoyancy forces and treat the end product of convection as being the background state about which we determine the equilibrium tide. And in that case, there are no buoyancy forces, and so in a non-rotating body, the momentum equation indicates that the tide is irrotational, so it's curl-free. So the tide is essentially a potential flow. And there's a famous equilibrium tide of Zahn, which actually doesn't satisfy this property. So it's incompressible, but not irrotational. And it turns out that's not likely to be valid in convection zones. But if you use the irrotational tide, then you can actually determine an equation for that, and it satisfies this second order ODE. And we can solve that with appropriate boundary conditions, and that determines the equilibrium tide. And essentially, it's just the flow associated with the bulge the moving bulge in the fluid frame. And this is likely to be thought to be the appropriate form of the equilibrium tide when the tidal frequency is not much less than the magnitude of the buoyancy frequency. So near boundaries, then this could break down. So when the tidal frequency is not much less than that, so it's in regions when the buoyancy frequency becomes larger, the square buoyancy frequency becomes larger, that this is likely to break down. So near the surface of the star in particular. So the idea to study the interaction between this flow and convection is what we do is we split the flow up into an equilibrium tide defined by the linearized equations I've just mentioned, and the convective flow. And what we do is look at the interaction between the equilibrium tide and the convection by looking at, if you're talking about an incompressible or Boussinesq model, which is what I'll mainly talk about. Well, in fact, that's all I'll talk about today, although we've looked at some anelastic cases as well. But in the Boussinesq problem, the only interaction between the equilibrium tide and the convection is essentially through the appearance of the tide in the nonlinear advection term in the momentum equation. So the idea in this approach is we fix the tide. It's time dependent, but we're assuming it's perfectly maintained, which is reasonable for the timescales of the convection, because the convection is much faster than the timescales on which the tidal flow will evolve, because that's normally on millions or billions of years. Then we can write down the momentum equation for the convection interacting with the tide, and the tide appears through the appearance of UE in these nonlinear advection terms, the contributions to the nonlinear advection term. So I'm not writing down the buoyancy and viscous terms explicitly. So we've gone through some work recently to look at these interaction terms, and essentially this one is the one that's dominant. And in fact, in incompressible models, it's actually the only one that's non-zero. So I won't go through the details unless anyone's interested, or you can see this paper below. So essentially, it's the gradients in the equilibrium tide and Reynolds stresses involving correlations of convective flow components that are responsible for energy exchanges between the equilibrium tide and the convection in incompressible models. And you can actually show these two terms as zero. So the angled brackets here are volume averages. And what I've done here is just take the scalar product of this equation with the convective flow to determine an energy equation for the convective flow, and taken a volume average or volume integral, and the tidal energy transfers are through these terms here. And in fact, it's only this one in red which is likely to be important. So we're going to look at that term in particular and in a simple way. And what we're going to do is we're going to now look to a local model where we're looking at a small patch of a convection zone of a star. And in the context of a local model, you can take the tidal flow as being linear in the spatial coordinates. And in the context of linear theory, we'll look at one component of the tide, and we'll look at an oscillatory shear flow. So we can look at an oscillatory shear flow that's in the x direction, well, in the y direction, but varying in x. And the key point for this, for the tidal problem, is it's going to be oscillatory, and we want to look at how the energy transfers depend on the frequency of the forcing, the frequency of the shear flow. And so we're going to model the equilibrium tide using this flow U0, which is linear in the Cartesian coordinates and oscillatory in time. And we'll probe the interaction between this flow and the convective flow by analyzing the Reynolds stresses involving correlations of the convective flow components. And so we'll study a simple model of convection, which is just Rayleigh-Benard Boussinesq convection, initially non-rotating. So we're imposing a hot plate at the bottom, cold plate at the top. And this oscillatory shear flow is the term that is non-standard for the Rayleigh-Benard problem. So there are a number of non-dimensional parameters. There's the Rayleigh number governing the strength of the convective driving. So in stars, this is going to be, well, it varies depending on where you are in the star, but at least 10 to the 15 in stellar convection zones. Whereas our simulations are, well, up to about 10 to the 6 or so. So what I'll illustrate is there is one regime in which we can make the extrapolation, or at least we hope we can make the extrapolation to astrophysics. So I'll come back to this point in a few slides' time. And there's the Prandtl number as well. So we'll treat the Prandtl number as being 1 just for to fix this for simulations, so they're more accessible. But we have looked at varying this parameter as well. So we've got standard impenetrable stress-free constant temperature boundaries in the z direction. In x and y, we've got periodic boundaries, except that we're using a basis of shearing waves to deal with the time dependence of the spatial dependence of the basic state flow u0. And so we actually use time-dependent wave vectors to do this, so the so-called shearing wave approach. So it's similar to what's done in accretion disks in local models of that, but this is in some ways simpler and in some ways more difficult because the flow is oscillatory in time. Simpler because you don't need to do any remapping. So if anyone's interested in the details of that, let me know. So the governing equations are these here. So theta is the temperature perturbation, u is the velocity perturbation, and I've written down these equations just in terms of the standard thermal timescale just for the purposes of the equations, although later on we'll reinterpret them in terms of convective timescales, which are more relevant for the problem. So the new aspects of the problem over the standard textbook case are the ones in red, which are the nonlinear terms involving the local approximation of the equilibrium tidal flow. And so this approach is quite similar to Ogilvy and Lisieux in 2012, but we've used Rayleigh-Benard convection rather than homogeneous convection, which has periodic boundaries in Z, because this has some peculiar properties that makes it not very well suited to this problem. So how do we define an effective viscosity? So we can equate the volume average rate at which the tidal shear does work on the convective flow with the viscous dissipation rate of the tidal flow by assuming an effective viscosity. And if you do this, then we can get a time average of this expression and get an expression for the effective viscosity, which is likely to be parameter dependent and also frequency dependent. And the larger this is, the more efficient you'd expect the tidal dissipation to be. And it depends on the Reynolds stresses of the convective flow, where I've dropped the subscript C when referring to the convective flow. And if you have a positive value here, it corresponds with the classical picture where the tidal flow is damped by its interaction with the convection. But it need not be positive, and in fact I'll indicate cases when we have negative values as well, which indicates tidal anti-dissipation. So when the convective flow transfers energy into the tidal flow, that's also possible in this system as well. So it's quite noisy to calculate this when you have turbulent convection, but we've ensured we have long enough runtimes to be able to determine this accurately. And we determined error bars based on I think it's based on 2 standard deviations away from the mean behavior. So error bars are going to be plotted on the next few figures, but initially I'll start with something simpler, where the error bars are essentially 0, because we're going to look at laminar convection. So we're going to constrain the box sizes so that we can have something that's laminar, where we just have a roll that's aligned with either the Y or the X direction, and this is going to be hot fluid rising and cold fluid descending in a roll-like pattern. So we chose this in this way so that we could compare with asymptotic theory and look for the simplest possible cases. And it turns out that in this problem, if you're looking at convection that's twice, 5 times and 10 times critical, the flow is very laminar, looks like the figure in the top right. And this is the effective viscosity as a function of frequency. And what we find is we find positive values for Y-line convection rolls. Initially, we find it's going to be frequency independent up to some frequency, in which case it transitions to a quadratic reduction in the effective viscosity. And we can also, because this flow is so simple, do an asymptotic expansion of the governing equations and determine analytically what this should be based on this roll solution. And that corresponds with the solid predictions, line predictions that we've got on the right. So this clearly agrees with the asymptotic theory, which is nice. So here I plotted things just using the thermal timescale units. So when you increase the Rayleigh number, you increase the viscosity and the frequency, so you can see things more clearly. But the convective frequency also shifts to the right because of that. So I'll show you a case when I've scaled this shortly, but this is just so you can see more clearly what's going on. And at low frequencies, very roughly, it's comparable with a mixing length prediction if you assume an RMS convective velocity, and if you take L to be the distance between the plates, then you get something with a proportionality constant of, it happens to be a 6th in this setup. Whereas clearly at high frequencies, you have a reduction in the effective viscosity, indicating that this mechanism is less efficient for high frequency tidal forcing. Interestingly, if you do also laminar convection, but you use initial conditions that excite an X-aligned convection roll, then you get negative values for every frequency. And this was a surprising result, so we looked into this in some detail. We redid the asymptotic theory and just verified that actually that also predicts negative values. So this isn't some numerical error. This is a robust result in this model. That actually in X-aligned convective rolls, you can get negative values of the effective viscosity. And more generally, depending on the convective driving and depending on the initial conditions, you can get negative values in this system. So the laminar cases are of at least academic interest, but are clearly less relevant for stars. So we also then turn to more turbulent simulations where we've actually got simulations that are independent of the box size in X and Y. So we've got large enough boxes that we have a turbulent state times supercritical. So these are not very high Rayleigh number simulations, but these are more demanding than if you just want to study the convection by itself, because we need to simulate these for hundreds of diffusion times in some of these cases. So some of these are very long-running simulations. And what we've done here is determined simulations in large enough boxes that we've got independence of the box size. So we have a sustained turbulent state where the properties are quite robust as a function of the numerical parameters like the box size. And this is showing this, essentially the same figure for simulations with various different Rayleigh numbers. It's showing the effective viscosity, but now normalized by the RMS vertical velocity times the distance between the plates. So that's comparable with mixing length velocities and length scales. And on the x-axis, you've got this now the scaled frequency, so that the ratio of the frequency to the convective frequency. And you can see that for very low frequencies, you do have something that's quite flat, but it's not flat up until of order 1, unlike the laminar cases. And then at high frequencies, we obtain something that there's some scatter, which is due to amplitude dependence of the tide. But apart from this scatter, essentially we have something that's robustly going as the 1 over the frequency squared for the effective viscosity. So this is consistent with the Goldreich and Nicholson reduction, although actually the reasons for this I'll indicate are probably not the same as they proposed. So there are several new results here. One nice result is the figure I'm happiest with, and I was very pleased with this when Craig showed me this. It's the figure I think is the nicest figure in his thesis, and in particular the reason for that is that if you look at these points, there are various different Rayleigh numbers that are overplotted, and you can see here that there's essentially a robustness as you vary the Rayleigh number. So it indicates that that a diffusion-free theory, so a mixing length-like theory, appears to be valid when describing this quantity. So there does appear to be a Rayleigh number independence of these results over this range. And there are some new results here. So one of them is that you don't have frequency-independent effective viscosity and to frequencies of order 1. There's an intermediate range here where we have a power law of -0.5, which is new. So this wasn't previously observed or theorized. And we've spent a bit of time trying to figure out what's going on here. One of the other interesting facts here is that the proportionality constant is not 1/3 at low frequencies. So it's something that is closer to 5 rather than 1/3, which is primarily because in convection, in Rayleigh-Benard convection, the horizontal length scales and particularly the horizontal length scales can be larger than the distance between the plates. And so I think that's likely to be the main reason for this being much larger than 1/3. But when you're applying this in stellar models, you often want to compare this with pressure scale heights. So it is relevant to compare this in terms of the distance between the plates. And there's a very commonly adopted tidal theory, which is the constant lag time theory. So this is assuming you have a tidal bulge, which is misaligned with respect to the line of centers of the star and planet by a constant lag time that is assumed to be independent of tidal frequency. So that's widely used in the literature, but we've shown here that actually it's not valid unless you're studying very low frequency tides. So it's only when the effective viscosity is flat here that model is actually strictly valid. And I've just indicated for reference the case for a hot Jupiter that I mentioned before, where this ratio is of order 40 for the eddies at the base of the convection zone. So we've looked in some detail at what's going on in these. And one thing we've found is that the frequency spectrum of the intermediate range, so this -0.5 power law, seems to be correlated with the frequency spectrum of the convection. So we plotted these are very long-running simulations of Rayleigh-Benard convection. Some of these are 1,000 diffusion times, which is only possible because these are not very supercritical. And we've needed this to get the low frequency portion of the frequency spectrum here. And what we've noticed from these is that there appears to be a correlation between the frequency spectrum of the effective viscosity and the frequency spectrum of the kinetic energy of the convection. So we don't have a good understanding of this, particularly because the asymptotic theory is not really valid for frequencies that are of order 1. But at high frequencies, this correlation appears to fall off, and then we move into the regime which we can apply this asymptotic theory to, where everything seems to go as omega to the -2. So there are a few things we still don't understand to do with the amplitude dependence of this, but the key results seems to be that when you're dealing with low amplitude tidal forcing, we obtain something which seems to be roughly independent of Rayleigh number when we obtain this. So there's some robustness to the profile, to the master curve for this effective viscosity. So we can look in detail at some of the interactions here to determine whether the old arguments of Zahn and Goldreich and Nicholson are valid. So the Zahn ones are, well, the idea that the effective viscosity is reduced, the arguments are clearly not valid because it predicts the wrong effective viscosity scaling. So what about Goldreich and Nicholson? So they claim that the dominant contribution for the interaction is from resonant eddies, so ones that have turnover frequencies. So they deal with a Kolmogorov cascade, and they're thinking that the dominant eddies that are responsible for the interaction with the tide are those with turnover frequencies comparable with the tidal frequency. So their frequency is omega of lambda that are comparable with omega, the tidal frequency. So if you adopt a Kolmogorov cascade with an outer length or a mixing length called MLT here, then we can determine how the length scale of these resonant eddies should scale with the tidal frequency. And what I've plotted here is results from a Fourier analysis of the flow, where we've looked at the dominant modes that contribute to the effective viscosity in the xy plane. So these are the integer wave numbers, nx and ny, on the xy plane here. And it indicates the modes that contribute provide the largest contribution to the effective viscosity. And what you can see here is that for these 3 different frequencies of tidal forcing, essentially it's always the energetically dominant eddies. So it's always eddies that are on quite large scales relative to the box, that always correspond with the peak in the energy spectrum, very roughly. These are always the ones that contribute the most to the interaction. So it's always the ones, the energetically dominant eddies that dominate, whether you're at low frequency or high frequency. It appears as if the resonant eddies don't play a role here. So if the resonant eddies played a role, you'd see a shift in this ring. It would increase with wave number as you go to higher frequency. And we have no evidence for that in these simulations. So it seems as if while Goldreich and Nicholson got the right scaling law, it's not clear that the mechanism they proposed is right. At least we've not been able to verify that in these simulations, even the more turbulent ones. Of course, it could be that you do get that if you go to even higher Rayleigh numbers, but I think that's probably not the case from the evidence we've got so far. So we've also done some work doing global simulations of the interaction between tidal flows and convection as well, using a spherical, well, an idealized model in which we have a spherical star for studying the convection, but we look at the interaction between that and a tidal flow, which in the bulge frame would make the fluid go on elliptical streamlines. So we've looked, while there's strictly a mismatch there, we can still look at the interaction here and look at how it depends on the boundary regions, and we find it's not sensitive to that. I won't go through the details of this, just to say that global simulations of this that are Boussinesque are driven by internal heating in a homogeneous full sphere also give something which is roughly compatible with what I've mentioned before, with some differences with the intermediate regime scaling, but otherwise consistent with what I mentioned before. One thing actually I realized I haven't mentioned is the negative values. Again, I dropped my talking about that here. So here I've shown on this figure, all of the points that are circles are positive values, and the ones that are triangles are negative values. And so what we find in these simulations that are more turbulent is that the negative values are actually only found at very high frequencies. And there's a trend, which is not so clear in this figure, but we've seen it more clearly in other figures, that as you increase the Rayleigh number, the critical frequency at which you shift to negative values tends to increase with the Rayleigh number. So the suggestion here is that the interaction in non-rotating convection, Boussinesque convection, with tidal flows and the convection, it appears as if it's always positive unless you're at extremely high frequencies, which are probably not relevant for astrophysics. So the effects of rotation may complicate that, as we've been looking at recently, but avoiding that complication, it appears as if you do get a positive value when you have a sufficiently turbulent flow for this effective viscosity. So I'll skip the details of the global simulations and just go to how we can apply this in stellar models to look at the consequences of this. So one thing we need to do this really is to look at anelastic or compressible simulations of this to determine how we can extrapolate the box size to real mixing lengths in stellar models. But we're going to make an assumption that the convective length scale is so the usual mixing length parameter times the pressure scale height, and we're going to call that equal to the distance between the plates in our model, which is essentially all you can do in the Boost-Ness model. And the convective mixing length velocity is comparable with the, or is equal to the RMS vertical velocity of convection in our system. So to do that, we can then fit the master curve from Craig simulations, and that gives you an effective viscosity as a function of frequencies that you can evaluate in stellar models. So you need to determine the tidal quality factor that results from this, you need to integrate up over all the eddies in a convection zone, where the eddies are slower at the base of the convection zone and faster near the surface. You need to take into account this, the integral of those over the convection zone, which is in this quantity d nu in the expression at the bottom. But if you have that, and if you have properties of the radius of the star and the tidal amplitude and so on, then we can determine, well, it's linear theories, the tidal amplitude cancels, but we can then determine the tidal quality factor, which is what we can then use to determine tidal evolutionary timescales. So the results from this, I looked at in some stellar models last year, is this is a function of the tidal period on the x-axis and the age of the star from including the where 0, I think it starts off at the pre-main sequence phase. So includes the pre-main sequence phase here, but I've only plotted from 1 million years onwards up until evolved stellar ages. So that's on the y-axis. On the x-axis is the tidal period. So for a hot Jupiter on a one-day orbit around a star, it corresponds with this red dashed line here. And the result for a solar mass star is that the tidal quality factor is of order 10 to the 10 for planets on one-day orbital periods. And that corresponds with orbital decay times of greater than 100 billion years or so. So the implication of this, which I'll extrapolate a bit from what I just mentioned, is that equilibrium tide dissipation is not likely to be important actually in pre-main sequence and main sequence stars and in giant planets because of this strong frequency dependence of the effective viscosity. However, it is likely to be important in giant stars and evolved stars, and it's probably the dominant one though. And the reason for that is you're often in a lower frequency regime of tidal forcing. That's one reason anyway. So just briefly, using stellar models, we can also look at the other mechanisms I talked about to determine whether they're important or not. And one of those is inertial waves in convection zones. So there are a lot of theoretical uncertainties about how you calculate the dissipation due to these waves. But there's quite a simplified way that was pioneered by Gordon Ogilvy in 2013. And he proposed a way of doing this by looking at, by determining a frequency averaged measure of the dissipation of these waves by applying an impulsive forcing. And essentially it means you can determine a frequency average measure of the dissipation of inertial waves through solving some ordinary differential equations. And that gives you a simple measure of the dissipation of inertial waves. So on the bottom, I'm showing a figure showing the tidal quality factor in some stellar models where we've looked at tidal forcing and solving the linearized tidal equations in a rotating convection zone of a star. And what we find is there's a strong enhancement in the tidal dissipation when inertial waves are excited, corresponding with these resonant peaks, where the tidal frequency is in the range -2 to 2 times the rotation frequency. And there's a lot of uncertainties about how the particular peaks will scale with viscosity, with Ekman number. But there's a more robust measure that can perhaps be made from these, and that's from this frequency averaged measure of the dissipation, crudely indicated by this blue line. And it turns out you can calculate that in a simpler way than the detailed properties as a function of frequency. And this has been done by many people in the past. So Stefan Matisse and his group have looked at this. And so what I did last year is accounted for the realistic stellar structure and looked at the frequency average dissipation of inertial waves as a function of the age of the star and the mass of the star. And what we find are plots like this. So for example, this is showing the tidal equality factor due to inertial wave dissipation as a function of age. And when this is smaller, it indicates more efficient dissipation. So this indicates that in the pre-main sequence phase, so less than about 10 to the 7 gigayears or so, the tidal equality factor is smallest, indicating this stage is the most dissipative for tidal evolution. But on the main sequence, we have a range of tidal equality factors for a fixed rotation period that seem to be roughly similar for a wide range of stellar masses. So I'm plotting here a range of stars from 0.1 to 1 stellar masses on the left figure and up to 1.6 stellar masses on the right figure. And so it seems as if between about 0.2 and about 1.2 solar masses, the tidal equality factor is of order 10 to the 7 when these waves are excited. And nicely, this is consistent with a statistical analysis of observations by Andrew Collier-Cameron and Moira Jardine a few years ago. So it's possible that this is consistent with their results and might explain why they found this when inertial waves are excited. Whereas in F stars, which have that are a bit more massive than the Sun, this mechanism is much less effective and that you have much larger tidal equality factors. And essentially the reason for that is related to the very low density of the convective envelopes of these stars. So this indicates that F stars are likely to be less dissipative than stars like the Sun. And I think in the interest of time, I'll only briefly discuss this. The final mechanism that I mentioned at the beginning was internal gravity waves in the radiated cores of stars like the Sun. And it turns out that this one is probably the one that's dominant for planetary orbital decay. So showing at the top right, I've shown a figure showing you the tidal response in a star. In the convection zone at the right part, you can see that it's just a smooth, non-wave-like response corresponding with the equilibrium tide. Whereas in the radiation zone, we have an oscillatory response corresponding with the excitation of internal gravity waves. And these waves are launched from the radiative convective interface. They propagate to the center of the star. And what happens there can determine how efficiently the tide is dissipated. You can see that the amplitudes are going up, which is due to the fact that, or mainly due to the fact that if you neglect damping of these waves, then the energy flux in these waves as you propagate to the center is conserved. But the volume is going down as you go toward the center. So the surface area of a spherical shell is going down. And so in fact, the amplitude of the wave has to go up to conserve the energy flux. And so it can lead to very large amplitudes being reached for these waves at the center of the star. And for roughly hot Jupiter mass planets, a few times Jupiter's mass around the current Sun, these waves can then break. And then simulations have shown that these can be efficiently damped. And in terms of tidal quality factors, you can get something that's of order 10 to the 5 for planetary orbits with one-day orbital periods. But if you don't like thinking in terms of quality factors, this drives hot Jupiter orbital decay on timescales of order of a few million years for a planet on a one-day orbit. And this is thought to be the reason for WASP-12b's orbital decay, although there are some uncertainties depending on the stellar model, which I can talk about if anyone's interested. And it may also explain why we don't have such efficient decay in WASP-18b, because that's an F star with a convective core where these waves don't reach the center. So I won't go through most of the details of this to try and not overrun too much. And just to reiterate, this is from evaluating all of the mechanisms I discussed. Equilibrium tides given by the black line here, based on the fit to Craig's simulations. Internal gravity waves given by the red line, and inertial waves, if they are excited, given by the blue line here. And this is giving the orbital decay of a hot Jupiter planet as a function of its orbital period on the x-axis. So a planet with exactly Jupiter's mass and a star that has a solar, is the Sun, almost the current Sun, with just a slightly different age. And this indicates that when the internal gravity waves are efficiently excited and efficiently damped, that this is the most efficient mechanism for damping for orbital decay of these planets. Whereas equilibrium tides is essentially irrelevant if our current understanding of tidal theory is correct on the main sequence. Whereas for binary circularization, it's likely to be inertial waves that are dominant, partly because inertial waves can be excited then because tidal forcing frequencies are less than twice the spin frequency of the star. This mechanism is likely to be the dominant one for both circularization of binaries and also synchronization of binaries as well. So inertial waves are probably dominant in these systems rather than equilibrium tides, as has been often considered to be a dominant mechanism. So I think I'll stop there to not overrun too much. So I've mainly talked about the interaction between equilibrium tides and convection in stars and planets based on first principles simulations, but I've also evaluated some of the consequences of this, as well as looking at inertial waves and internal gravity waves in stellar models. But there are many uncertainties in tidal theory, and in particular, I'd still say that the interaction between turbulent convection and tidal flows is still probably one of, if not the most uncertain tidal mechanism. And we really need more realistic simulations in more realistic stellar models to look at this, such as anelastic models, to study this in more detail. And also the inertial wave mechanism, there are a lot of uncertainties I haven't discussed, which need to be looked at in more detail. So more work is needed on that problem as well. So I think I'll stop there and see if anyone has any questions. So thanks for listening.